Good morning, everyone. Let's start. Um, are you able to hear me clearly and see my screen?
Yes, sir.
Okay, thank you.
Recording in progress.
Okay, good morning. This is the second lecture in oscillator circuits, section 1. Last week, we started with oscillator circuits. Let's look at the feedback circuit point of view. You have learned negative feedback circuits, right? So basically what we do, we have a feed-forward path with amplifier gain. A is an amplifier. Generally, it is denoted by a symbol, amplifier symbol with gain A in the middle. And then output, E out. We have a feedback path where feedback gain is beta. And then it is a negative feedback system, therefore we subtract the feedback component. The positive feedback system also can be analyzed by bringing the minus to beta. So beta becomes minus and then it becomes plus. Therefore, output sample is given as an input. But in the oscillator design, we don't have any explicit any external input, right? All we have is we have an amplifier and then output is sampled with set1 and set2 and given a fraction of output given as an input. So if you go back to basic feedback circuit, Vi here external input is 0. Right? So we have a feedback, a positive feedback system. Therefore, beta is we have only negative positive feedback system, but if we substitute beta is equal to minus beta, which becomes a over 1 minus a beta, right? We can derive from positive feedback response from the negative feedback system by substituting beta is equal to minus beta, so that minus into minus becomes plus, right? Therefore a1 minus a beta. So the loop gain going to be a over 1 minus a beta. Now what happens? A beta becomes, now in the positive feedback it becomes 1 minus a beta. What happens? A beta less than 1, equal 1 and greater than 1. The greater than 1 is the unstable condition. Okay, now if you go back and look at it, what's the feedback? B out divided by set1 plus set2 into set2, right? So we can gain of the A beta has to be 3, little bit lower than 3 or little bit higher than 3. So when it becomes A beta greater than 1, because 1/3 is coming there, 1/3 is coming because of this RA of RB is equal to 1, and it becomes 2. So gain becomes 3. So that's why A beta becomes 1, gain is 3, so beta becomes 1 over 3, like that. Now, if gain is greater, exactly 3, then we have oscillations. That's where the S is equal to j omega case. Sigma is 0 here. We have to make sure the real part of the sigma is 0. The real part is less than 0, e to the power minus sigma. Then there's an amplitude, oscillation plus amplitude, which causes the e to the power minus t. So you can see the amplitude is reducing with the time. So this is a transient response. Now when it's greater than 3, amplitude increasing and it's goes to unstable, or it's a amplification is clipped between VDD and ground. So we use this instability by exactly putting A beta is equal to 1, right? Now, according to the gain, because we already have a relationship between RAO, RB is equal to R1 plus R2 C1. Sorry, RAO, RB is equal to R1 divided by R2 plus C1, C2 divided by C1. If you take R1 is equal to R2, C1 is equal to C2, it becomes 2. That's a simple implementation. So RA is 2 times RB. So the gain going to be 3. 1 plus RAO RB, 1 plus 2 RB divided by RB, which is going to be 3. That is why A beta becomes 1 or beta becomes 1 over 3. Right. So basically beta is, we have a fixed value by choosing R1 over R2 is equal to, sorry, R1 over R1 is equal to R2, C1 is equal to C2. So beta is fixed here. Therefore, by changing the gain of this amplifier, how we can change? By introducing a variable resistor here or here. You have to carefully choose the variable resistor. Now, according to this, gain is RA over RB. So RB becomes 2RA. So 2RA is bigger. Right. So what we can do, we can take 1 kilo ohm for RB and 1 kilo ohm fixed resistor for RA, probably 2 kilo ohm variable resistor. Or else we cannot choose 2 kilo ohm because we cannot reduce below 2. So 1 kilo ohm, 1 kilo ohm plus 2 kilo ohm. Therefore, maximum RA can go to 3, minimum it becomes 1. Sorry, minimum 0. So the gain minimum value is 1. Maximum gain can be 4. So the gain, variable gain between 1 and 4. This is a design concept. So you cannot put simply a one simple variable resistor here. Okay, that also sometimes bring the issue because we are simply connecting, if there's you are simply connecting the output voltage to the input. Therefore, we need to take some precaution. So always good to have fixed resistance plus variable resistance. Ideally, if you want to keep G is equal to 3, please note that last time we talked about, we talk about A beta by changing, but we had to do is we had to fix A beta is equal to 1. So we had to have some flexibility, but we cannot have flexibility in the beta because beta is decided by the oscillation frequency. We had to fix omega by choosing the appropriate R and C, and therefore we are playing with the gain A. Okay, we are playing with the gain A. So if you want to play with the gain A, that means A is variable. So op amp plus RA/RB decides the amplifier gain. Therefore, since RB is RA is bigger because it's 2 times of RB. But again, what will happen if you lower the resistance? Why I had to choose 1K? Why not this 10 ohm, 10 ohm, and then 20 ohm? Still, you can satisfy this ratio, but power consumption will be very high. It will bring so much current through this. So power consumption high. So where do we draw the limit? Then why we cannot have 1 mega ohm, 1 mega ohm, and 2 mega ohm? There is another limit set by the inverting input current. We had to see how much current this op amp takes, how much current through its inverting input. non-inverting input. So if that is 1 microamp, 2 microamp, then we have to make sure that is the current through this path is at least 100 times. It has to be less than 1%, because RA-RB act like a potential divider here. Agree? That is what our, you see, V minus S equal to V out is in RB divided by RA. What is the assumption in this when writing this equation? We ignore the current through the inverting terminal. Right? Then only we can write like this. So in order to have the first and second equation valid, current through the inverting terminal and non-inverting terminal is negligible, less than 1% compared to the current in the relevant path. So for example, inverting terminal current, if we assume non-inverting inverting terminal current almost same, say if it is say 1 microamp or 2 microamp, then we have to have 1 milliamp at least here, or at least 0.5 milliamp. Okay, less than 1%. So if you want to have 0.5 milliamp, then what's the supply voltage? Op-amp supply voltage, minimum supply voltage, maximum supply voltage. So you have to choose one. That's why op-amp selection also matters here. If you choose arbitrarily, then what you do, you are compromising your power consumption. So when you choose op-amp, you have to choose the right op-amp. But in the laboratory, we may already choose the op-amp which is appropriate for you, because we have to keep the components available. Right? We have to keep the components available. You can choose any op-amp and you come up with one model. And if it is not available in the department, then how to do the practical? Therefore, in the lab sheet, they already decide which are the components to be used. Right? But again, since RA, RB are the resistors, you have to design it. Right now, every group will have to come up with different frequency range. Depending on your index number, most probably you may have to come up with different frequency range. So two group design will not going to be the same. Procedure will be the all groups will have similar procedure, but values are different. So you have to calculate for your required frequency. And then how do you approach? Because this module is why I am spending this much of time to this particular section. This module is analog circuit design. We are looking at some concepts or some ideas in the designing part. So I am trying to explain how to do the design. Okay. Now, what are the other factors we need to consider? How do you connect the circuits in the lab? First step, you do the calculations and you come up with the capacitance, resistance values R1, R2, C1, C2. But it is okay to choose. Last time we remember we have proved that oscillation frequency is equal to 1 over omega 1, omega 2. Right? I think we here. Yes, because here we have chosen R1 is equal to R2 and C1 is equal to C2. But how do in the lab, how do you do that? You have to measure the R1, measure the R2, and substitute to this equation your desired frequency, maximum, minimum, and you can choose the capacitance accordingly. But again, in the lab, you are not going to be asked to design one particular frequency, range of frequency. So what do you do? Range of frequency means minimum frequency, maximum frequency, right? So it is not advisable to change the capacitors. What you can do is you can take two capacitors, same capacitors, because so we C1 is equal to C2, but keeping R1 is equal to R2 is difficult because now we have a range of frequency, minimum frequency, maximum frequency. So maintaining R1 R2, R1 is equal to R2 relationship is difficult, even though the textbooks or my lecture note says. In the lab, we have different function. Therefore, it is not advisable to use variable resistor to R1 and R2. The idea is we keep R1 or R2 fixed and we let the R2 change. R1 or R2 change. Anyway, relationship is going to be changed now. 1 over square root C1, C2, or we can take the C out. So therefore 1 over C square root R1, R2. So you keep R1 to some value, R2 to another. Again, you have maximum, minimum. So you have to calculate appropriately what is the fixed value of R2. Suppose if you decided to change R2, what is the fixed value of that and what is the variable component of that by considering maximum, minimum of the oscillation in the lab shade. That is maximum, minimum is different for different group. Therefore, your calculation going to be different. Okay. So we have some additional points today, how to do the lab. And also, what would you do if you want to increase the frequency to maximum frequency? So if you look at the equation, F is equal to 1 over 2 pi C square root R1 R2, you can bring the C down. That means when you reduce the capacitance, the frequency will increase. But again, with some limit, it is difficult to go beyond certain limits because the parasitic capacitance, we are using standalone components with high tolerance. Therefore, parasitic values will take some effect. And also, when you try to reduce C1, C2, R1, R2 to increase the frequency, what will happen? The negative feedback, the positive feedback path, where we have complex impedance Z1 and Z2, the current through the positive feedback will reduce, isn't it? When you reduce the R1, R2, C1, C2 values, the current through the positive feedback is reduced. Then what happens? It becomes comparable to the non-inverting input current. Therefore, the first relationship here fails at that point. Therefore, if you want to increase the frequency further and further, you have to carefully choose the op-amp so that the inverting current, non-inverting, even though we assume that is zero, but in fact, what we do, we neglect those current compared to the current in the path. But when we bring the circuit current in the path comparable, then that is where we reach the maximum oscillation, right? So not only that, then if you want to increase the maximum frequency, what we have to do, we have to make sure that these two currents have minimum as possible. 2 microamp, you can go up to 1 or 2 nanoamp. Then you can bring microamps here, or even 0.1 means 100 microamp, 0.1 milliamp, 100 microamp here, then that will oscillate fast. Remember, capacitance has to be reduced, resistance has to be reduced in the positive feedback. The other one is designing the amplifier. Look at the characteristic equation. Ratios matters here, not the actual value. So RA, RB in mega ohm or kilo ohm, R1 not to be in mega ohm or kilo ohm, it doesn't matter. As long as the ratio is maintained and we have this relation governing equation relationship, that is fine. C1, C2, nanofarad or microfarad doesn't matter. Why? The the if it is microfarad, that will be cancelled out. Nanofarad, that will be cancelled out. Eventually, C2 over C1 ratio matters. Right. Therefore, the current through the C1, C2, current through the R1, R2 should be, but again, we have one condition here. Current through the C1 is equal to current through the R1. The problem comes when current through the C2 and current through the R2 can be different. Okay, therefore, current through these components is much higher than the current going to the non-inverting terminal of the op-amp. So these are some of the checks that you can do. So if you want to do oscillator design, you take one breadboard, get all the components, connect the circuit, and observe the output is not the approach. What you have to do is first you do all the required calculations, select the component carefully, make sure the components value that limit. For example, if you choose 1 kilo ohm or 2 kilo ohm, just measure first using multimeter, measure the resistance, whether it has that range. If it is plus or minus 10%, the resistance should be within that range. Or else, because we have some faulty component also in the basket, and you can have to measure the op-amp performance. How do you measure it? Simply use RA and RB and op-amp alone. Then it becomes non-inverting amplifier. Just give one sinusoidal waveform to the plus terminal and then measure the output and see whether you have the amplifier functionality correct with the RA-RB magnification factor. Then your amplifier is ready. You have to check component by component first. Do not simply go and connect all the circuits in the breadboard and observe the output. Okay, that's a step by step you progress. Otherwise, what will happen if you connect the component or everything out in the breadboard, and if you observe the output, if the output is not as per the expectation, then you will have huge debugging time. If the amplifier is not working properly, then we have only 3 components here: amplifier, RA, RB. You have already measured RA, RB. So if it is not working properly, obviously the problem is with the op-amp. Right. So you can either change op-amp or you can request for a new op-amp, whatever your solution, the approach of designing analog circuit. You will enjoy it if you do it in a right way, and it's manageable steps. Okay, manageable steps. Measure the capacitance value also, whether within that range. Okay. Now remember, output oscillation frequency also depends on these values. The range, if you want to increase the range, say I want to have some oscillation up to 60 kilohertz, 80 kilohertz, then you have to consider all these in non-inverting, inverting current through the path and all these things. Those groups will get 10 out of 10. Right. Anyway, I will come and check how you perform in your design. It is very simple, but important when you go to the labs, you have to follow the certain approach. Remember, education in Sri Lanka is free. If you want to learn the same thing in overseas, you have to pay in lakhs. Okay, so simply because everything is free here, do not ignore it. Respect that the knowledge, respect the thing that you study. You don't need to respect others, you respect yourself. Respect that you're learning, your knowledge gaining, and try to enhance that day by day. Okay, try to optimize that, because after semester 8, Nobody chase you and teach all these things. How to do the lab, then you are on your own. Every mistake that you make here, if you fail to rectify it, if you go to the industry, you will pay high price to rectify that or even to detect that. Therefore, try to get the right background. Okay, try to have a good discipline in the labs, right? Try to maximize your gaining there. Experience, hands-on experience on how to operate those oscilloscopes, power supplies, basically signal generator, multimeter. What else you are going to use, right? Enjoy that. Circuit design, electronic circuit design is enjoyable if you have the right mindset. Right. So, and application wise, now you see, one thing we should note, if I want to introduce minus sign beta, I can bring it through phase shift also. Right. That is why negative, because forward path gain is real, isn't it? In our case, in the op-amp inverting amplifier, there's no complex path here, so it is gain is real. But the beta may introduce phase shift because beta is complex. This is real. This may introduce complex, but in the feedback system, it can happen anywhere. Sometimes forward path can be complex, beta becomes simple integer or simple number, fraction, real fraction, but A can introduce some complex. Complex means what? When you have capacitors resistance, there will be a phase shift. So we have to observe the phase shift, and if it goes beyond 180 degree, then what happens? The phase shift introduces another minus point, right? That becomes negative feedback system. Okay, that becomes negative feedback system. Therefore, phase shift also important, but I'm just talking in general. But here we don't need to observe anything because we make sure that by adjusting the variable register, we make sure that A beta is equal to 1, because by the time when you have steady waveform, steady sine waveform, that is the place where we can make G is equal to 3. So that is where we get pure sine wave. Now, it's not only the understanding the sine wave, but also you see in the S plane how it reacts. This is where exactly the solution is in the imaginary axis. S is equal to j omega. That is why in steady states, S is equal to j omega replacement is done. If there's a sigma, either it is plus or minus, it is not a steady state response. This is unstable. This is transient response. Either way, in the steady state, it will not therefore. That is why in most of the places you replace S is equal to j omega. Okay. Right. Now, again, what sort of analysis here? This circuit is just for your information only. You don't need to implement or prove anything. Just if you have time, you go through this one and see how does the phase shift can happen in this circuit. But which elements are limiting the performance, maximum oscillation? Right. Now you can see here also we had to make sure R1 over R2, right? See complex Z1 over Z2, right? But however, the current through this is challenging. In op-amp, we can clearly say I plus I minus roughly equal to 0. And we had to make it to 0. There's no such thing called 0, right? At least there's some minimum current, but compared to the external path, that is negligible. Okay. Now, here, obviously the limiting factor is the base current of the Q1 and the current through this one. Anyway, the current through R5 will flow through Q1 and we have some external voltage here, assuming that there's no current through this path. But we have to make sure that it is happening. Okay, so how do you make sure? You connect a series resistance here and measure the current voltage across the series resistance and see how much current flowing through that resistor. Or you can observe the waveform also using oscilloscope. Right? But anyway, it is not for the lab. It is just for your thought. Right? Amplifier. There are two stages. One stage not sufficient. We have discussed that. Why it is not sufficient? Because gain becomes negative. Gain becomes negative. So we have to make positive feedback. Right. Here in relaxation oscillator, what are the assumptions that we take? Same assumption. I plus I minus equal to 0 compared to the path. Right? So RC, actually the product of RC matters. So R can be higher. Okay, for example, 1 microfarad, 1 kilo ohm, and 1 microfarad and 1 kilo ohm, and 1 nano ohm and 1 mega ohm. Sorry, 1 nanofarad and 1 mega ohm. Going to be the same value, RC, when you, and the 10 to the power 3 can be incorporated into C or R. Right. So, but what is the impact? The point is, when R becomes higher and higher, the current through this path is getting smaller. And it is negligible, not negligible, it may not be negligible compared to the current through inverting terminal. So here it is acting as a op-amp. Sorry, acting as a comparator. The R1, R2 and op-amp is acting as a comparator. Is compare the V minus voltage. So here we have a positive feedback as well as negative feedback. Right. Positive feedback as well as the negative feedback. So the charging discharging curve goes to the negative feedback. Okay. So some blinking lights and electronic beepers are the applications using this one. You can create some beepers or some electric blinking lights, right, when necessary. So how do you handle the supply voltage now? Here we have to have dual power supply if you say this is ground. Or else you may have to have a 0 to 5 volt and 2.5 volt is the mid value. You had to use another potential divider, 2.5 volt, or Zener diode at the mid value. If you use Zener diode to get a reference midpoint, then the power consumption through the Zener diode has to be considered. Right. And again, Please develop the concept. Give me a minute, please. You can
Recording
hear
in
me now?
progress.
Are you able to hear me?
Yes, sir.
Okay, good. Right. So, so the time constant RC, when you calculate, you can reduce the R and increase the C, or you can reduce the C and increase the R. That depends on, that is going to decide the current on this path. So it is not that you can choose any component you like. You have to make sure that the current through this path is significantly higher. That means at least 100 times higher compared to current through this. Why 100 times higher or more? If I see 1,000 times, that means I am restricting too much. Okay, that means 0.1 percentage. Anyway, we have to tolerate the capacitor resistor tolerance at least 5% or 1%, isn't it? If you talk in general, resistance can be 10%. But if you choose go for SMD components, probably you can go for 1%. So when capacitance resistance are 1%, what is the point that we have 0.1 percentage accuracy on this one? It is something like you are preparing cup of tea, having very high quality tea leaves and medium quality of sugar. What's the point? Same thing here. Since we are talking about 0.1 percentage, sorry, not 0.1, 1% minimum, right? 1% tolerance components. And in this path, if we are maintaining 1,000 or 0.1% accuracy, it doesn't make any sense, right? Therefore, you bring it to that level. If you use medium quality tea leaves, medium quality sugar. If you want to use high quality tea leaves, high quality sugar. Simple. Otherwise, the highest tolerance will take over, will decide the performance of the circuit, whereas the effort that we give for the low tolerance design is submerged within that high tolerance effect, right? Therefore, you had to be little bit, you had to pay a little bit attention to this matter also, right? Because it doesn't bring you any goodness in the circuit. When you have plus or minus 5% tolerance components, if you go for amplifier with 0.1% accuracy, probably it is easy for your calculation, but output performance doesn't make much sense, right? Right. So relaxation oscillators application is blinking lights and electronic beepers. You also can come up with this. But the problem is when you switch on the power supply, most of the time you don't focus on this. But because we use in the lab, we use power supply, which is connected to our AC outlets. But when it comes to handheld device, when the circuit is idling, giving power to that is waste of energy, right? Therefore, when we need it, we can turn on the oscillation. When we don't want it, we can switch off the power. Therefore, the power switching is important. The power, but here, I mean, if you want to go for an extension, how you can switch the power? You can check the amplifier current, how much current it needs, right? And then you can put a transistor MOSFET in series. Either one side is sufficient, probably the VDD side, right? We have footer switch, heater switch. Heater switch means close to the VDD, footer switch means close to the VSS. We call it power gating. The power is given to the VDD, VSS power is there, but power to the op-amp, to this circuit is given only when it is needed. If you have a transistor between this VDD and the positive terminal of this op-amp, but transistor is a P MOSFET. You have to have a P MOSFET here, not N MOSFET, because N MOSFET means the problem. P MOSFET, because it's close to VDD, N MOSFET we connect to, which is close to ground. Okay. So then we can have a power gating. When you control the gate, when you lower the gate in the PMOS, low means put ground voltage to the PMOS, output get connected. Drain and source get connected. This act as a switch. Okay. So here we are not talking about that. We can slowly increase the discussion. Right. Okay. Let's take a 10 minutes break and continue.
Recording stopped.
Okay, let's.
Recording in progress.
Okay. So challenge yourself to get a maximum oscillation frequency with a reasonable quality in your waveform. Well, it is not, I think, part of the continuous assessment, but if you have time, I strongly encourage you and connect it in the breadboard. As I mentioned earlier, the design concerns, how do you connect? Don't put all the components there and check the output. That's not the right way. The first thing that you should do is, how many blocks we have? We have one capacitor, one resistor which decides the charging, discharging, and we have one comparator. So the first thing is you connect the comparator. You observe the inverting input current, non-inverting input current, and make a note and choose the right op-amp. Select appropriate resistor. Remember, R is too low. Suppose if non-inverting current is 2 nanoamp, right? Input current to the op-amp is 2 nanoamp, and you have 1 milliamp in the resistor path. It is not optimized, right? So roughly you can have about 100 times higher. It is 2 nanoamp. I mean, it is not the typical value. Please note that you have to consider the maximum value. Okay, maximum value has to be less than 1%. Suppose if maximum is not available, you can consider typical, and you have some safety margin. Say if the typical is 2 nano, you can consider 5 nano is the maximum by yourself. You have to write that assumption. Okay, I consider 5 nanoamp as the maximum, and therefore 5 times 100, 500 nanoamp, 0.5 microamp. You can, no harm, you can go for 1 microamp, because 1 microamp into 5 volt, anyway, 5 microvolt, which is negligible power consumption. You have to have right justification. I'm just estimate. Okay. So selecting this resistance, right? And there can be some deviation. Suppose if these two are plus or minus 5% or 10%, even though you choose 1 kilo ohm, 1 kilo ohm, or 1 mega ohm, 1 mega ohm, well, what is the maximum minimum deviation? I think we have already worked out in the last lecture. It is R1 over R2 into R1, then you bring the R1 down 1 over 1 plus R1 over R2, and then you get the maximum, minimum, all those things, right? So depending on depending on the tolerance, you will get the maximum, minimum value. So that is what it's going to affect the output. Now that is one thing. Another is the current through this one. There can be some deviation here, right? Because why all these analyses are important in design? Suppose if we want to improve the performance, which one you will change? What modification you would do, right? So we see all the possibilities, all the deviations, and it is affecting the output. And we come up with which deviation contributes to the maximum deviation in the output. Is it the resistor tolerance, or is it the selection of value, or is it the op-amp input current ratings, or selection of supply voltage? which one brings the maximum deviation in the output or maximum error in the output, if we put it in a simple term. So we target that particular parameter, which brings the maximum. Okay, we cannot simply go and ask, otherwise we don't know what to do. Suppose if somebody asks, okay, now it's giving a very good output, right, 20 kilohertz, change it to 30 kilohertz. What would you do? Right, that is where this analysis is important. And this analysis is not all in one writing mathematical equations. Block by block, what are the blocks we have? If you break down the comparator, you will have one block, one operational amplifier as well as one potential divider, two resistance in series, right? Therefore, you break down block by block and try to analyze the effect. And we hear how many blocks we are trying to connect it. 3 blocks, in fact. One is potential divider, another op-amp and potential divider becomes another block, which is the comparator, and charging discharging path becomes another block. Right? 3 different blocks. But most of the time what happens, we put all the components in the breadboard and try to see where the output is coming. Right? And then we spend some time on that. If the output is not happening, then we write whatever we think is correct and then in the lab session. That is not the way to approach. Try to challenge yourself to debug. So the debugging skills need to be improved, and that those, in order to improve those debugging skills, you have to analyze block by block. Okay, block by block and the integration part. For example, how do you integrate this potential divider and op-amp? Through this non-inverting current, isn't it? And then how do you integrate this comparator to this charging, discharging? Again, inverting input current. Right. So all this has to be properly analyzed. What are the assumptions involved here? Non-inverting input current is negligible to the feedback path, positive feedback path. Inverting input current is negligible to the negative feedback path. We have positive feedback and negative feedback here. As long as the operational amplifier is concerned, you have both positive feedback and negative feedback. So which should work better, or which should work the higher frequency? Op-amp and the feedback path, positive comparator should work compared better. That means comparator bandwidth should be higher comparing to the oscillation frequency here. Right? Right. Question: how do you change the charging, discharging time? How do you change the charging and discharging time? Now, if you look at this circuit, charging, discharging, because we are comparing the voltage V minus, right? Charging happen through R and C, and discharging again happening through R and C. How we can change the path? Because we can connect only one resistance. Any modification do here is equal to both charging and discharging. Therefore, charging time constant and discharging time constant going to be the same. Right? How you can change it? We can have two similar resistors or two different resistors with the diode in series. Obviously, diode forward voltage going to have some effect here, but again, if we carefully design it, when charging it, we use one path. When discharging it, we use another path because there's two diode in opposite direction. Right. That way we can separate the charging and discharging. But again, there's another issue popping up, that what if the supply voltage is not sufficient? So we have to carefully decide the supply voltage of this op-amp so that the diode drop is, the effect of diode drop is minimized. Otherwise, if it is a 2 volt, the diode drop is 0.7, it is going to have some serious effect in the performance. But again, you can design. Okay, you can design. It's a charging and discharging. So how is the charging and discharging? How you can consider the diode drop? Simple. If the output, assume that the output is switching between minus VS and plus VDD, or VSS between VSS and VDD. So the new output going to be the same because the output is going to controlled by the op-amp, but however, charging discharging voltage is not to V out, but V out minus VDD. Agree? The current is flowing through this. The voltage across the capacitor and resistor is V out minus VDD. Okay, so it will not go to the beta, will have some effect. Non-linear effect here, but anyway, the effect is similar. So, for B plus and my B minus will be the same effect, is similar. But anyway, you can work out that. Right? Charging and discharging path is different. The supply voltage to the charging and discharging path is not V out, but instead V out minus VDD. Sorry, V out minus VD, diode drop. If you put the diode here, two resistors for the charging one path, for the discharging another. Right. Why we talk about ring oscillator? Because this is where you can implement in silicon IC, right? If you have interest in fabricating some silicon ICs, I can guide you. You can design this one, right? Here capacitance is a dummy load. If you want to have dummy load, you can put reverse bias PN action here, right? Reverse bias PN action, charging, discharging for the charging, discharging part. However, you also can put another inverter input, but that inverter is output is idling. But it is good in some way because we can tap different outputs. Okay, can tap at different outputs, and you also can have some control when it is enabled. It oscillates. When it's not enabled, it will not oscillate. So what do? You put a switch here or put a AND gate here, right? Somewhere in the feedback path. If you put an AND gate, right? One input is the feedback path, other input is the control, enable pin. So if the enable pin is 1, then output is input is output is equal to input. If it is input is 1, output is 1. Input is 0, output is 0. It keeps oscillating. the enable pin is 0, no matter what the output is, input is 0 always here. Therefore, V1 is static, V2, V3 is static, V4 is static, and therefore output is static. So that way you can have some control. But again, what is the bigger issue here? The issue is different loading. When I put AND gate, loading of the AND gate is different. So therefore, output of the loading for the first inverter output has a different loading, which is the input dummy capacitance plus input capacitance of these transistors. Second inverter will have the same like first one. Third one will have the different loading because it has the AND gate here. So we need to connect odd numbers of inverters. How do we decide the odd numbers? Why we have to have different numbers? Because the delay, if we choose one particular process, for example, you want to use a tiny tape out free of charge, right? Now you can do simple design. If you plan it, you can do that as a first lab, and you can tape out, and when it is oscillating, you will be very happy because your design actually works in silicon. Remember, no matter how complex design you have, even if it is not working in silicon, nobody cares about that. If you have simpler design, if it is working in silicon, people appreciate you a lot. So even though simple design, bring it to the silicon. Working silicon matters here. We call it silicon proven design. It can be simpler design, but it is silicon proven. People will trust your design. People will trust your work. So people will not understand the complexity in many situations. So you can say, I have designed a clock which output frequency can be controlled, and it has the enable pin, then it brings a reasonable complex to semester 5 students. How do you bring different speed? All you have to do is, because remember, if you go for a certain process, delay is constant. If you take an inverter, delay is constant. Or else you have to change the transistor size. When you put the bigger and bigger transistor size, the delay is different. Or else what you can do, you can decide how many delay gates you are going to put, either 3, 5, 7. The more delay gates that you put, more more propagation delay. More propagation delay means less frequency. Agree? Therefore, number of less elements. What's the minimum number of elements that we can have? Only one inverter. One inverter. So input is equal to output. This is oscillation, feedback
Recording in progress.
Simple design. All you have to do is you have to short this. You have to short this. Okay. You take the output. Where do you get the feedback from? From this one or this one or this one? In that case, we have to use tri-state logic. I will talk about that in the next session because I don't want to put too many things at the same time. So if you are interested to do some tape out, trust me, if you do some silicon proven design, it takes your CV to a different level. You can easily get a job, IC design job anywhere, because that brings high reliability to your work. Okay, so if you are interested, you let me know. But this is completely digital. Okay, so what we are going to do is variable oscillation, variable frequency oscillation. Or else what we can do is we can use three inverter. Using three inverter, we can create a stable clock, and we can use registers. Register means, sorry, D flip-flop to divide it. But remember, dividing means F divided by 2, F divided by 4, F divided by 8. Division. We bring a high frequency clock and divide it. But increasing delay changes the frequency, because 3 inverter delay is different from 5 inverter delay. It is not divided by 2. We cannot take 4 because 4 is stable circuit, right? Input becomes output. Our A beta is not equal to 1. But 5 odd numbers of inverter, either 3, 1, 3, 5, 7, 9, 11. You can go. You can come up with some idea. Or if you do not have idea, you come and see me. I will tell you how to do that. Supply voltage is going to be the same, right? We can come up with a simple ring oscillator design in silicon. But you have to let me know before end of this week, because we have to prepare, because we have limited time. The next step out, we need to include this. Don't go for very high complex. I mean, if you want, you can go, I don't mind. But generally, failing in silicon using high complexity design. On the other hand, successful low complexity design implementation, the second scenario is better, because silicon proven word is different level. Right. So again, I talk about 3 inverters today also. Last session also I talk about the same inverters, but the discussion points are different. The reason why I deliver my lectures like this is to keep adding information so that you can digest easily, right? It doesn't mean that the same lectures are repeated, but we keep adding points on top of what we have learned last. So introduction to 3 different oscillators. One is digital, other first two are the analog. And then these are sufficient enough to understand the oscillation part, right? So that concludes my section 1. Weak bridge oscillator design concerns, component tolerance, frequency of oscillation, applications, ring oscillator design, characterization, limitations, and circuit simulations. Right? So lecture part is over. Now we are going to do the laboratory part that is pending. So you can start doing when the university physical activity, when university resumes the physical academic activities. So in the next session, we will be talking about current source. Again, I have something more to discuss here. Applications of Wien-Bridge oscillator. The applications are primarily test and measurement side. How do you generate a ring how do you generate a tone? Normally, when you design amplifier, what will be the input to that amplifier when you do the testing? It is sine wave, right? If you do not have a signal generator, how do you do that testing for simple circuits? You can generate a Wien-Bridge oscillator with one op-amp, very low cost. You can design it. That is why in this lab, in your first lab, you are going to design Wien-Bridge oscillator, which give you a range of frequency to give you that impact. Okay, so primarily it is test and measurement purpose. And also you can give tone noise. If you want to do some kind of noise measurement, how do you generate tone noise or jammer? Right? Basically, the ring oscillator is useful to in the test and measurement side, and also signal generation, audio equipments, right, to measure the signal and noise ratio. But low distortion sinusoidal waveform, it give you a clean, almost near ideal sinusoidal waveform. But you can use the rectangular waveform and use the filter to get a first harmonic. That helps, but still you cannot eliminate the other harmonics. Therefore, compared to that, this one will give you low distortion sinusoidal waveform. Okay, so these are the applications that we can think of. And also tone generator, right? Beep tone, no, not this beep tone here, but this is a tone generator, on and off. Then used in distortion testing of power amplifiers. Distortion testing of power amplifiers. Used to test and measure capacitance values. Yeah, this is one of the important. Fortunate that I see the last point, otherwise I would have forgotten that. Capacitance measurements. How do we measure the capacitance? Well, if you go and characterize this, right? Now what we are going to do, we are going to have our local capacitance here and get the output frequency. We design a Wien-Bridge oscillator, characterize it, and we have a curve. Okay, by changing this capacitance values, what is the frequency we have, right? You have plots. Then what you can do, you can bring your own unknown capacitance, place it here, get the output frequency and project it, and you will get the capacitance value, right? That means we do backward calculation. We know omega, therefore what would be the C1? It's like Wheatstone bridge. Remember in A level, Wheatstone bridge? In Wheatstone bridge, you used to measure resistance, unknown resistance value, to make the midpoint, current through the midpoints to equal to 0. By making that, you can have R1 R2 is equal to R3 or R4, whatever the equation, relevant equation, and then all three resistance we know, we have unknown resistance. Same fundamental here, you can measure the capacitance. We cannot take the capacitance measurement meter or this power supply, the bulky items to the field. Right. For example, you want to measure the capacitance between two plates. How do you do that? In the field. The field means, okay, in the top floor, you want to do some testing. Or in the paddy field, you want to do some testing. We cannot take all these equipments, bulky equipments there, and we getting the power supply to those equipments are difficult. So handheld devices, battery operated devices, you can simply come up with this Wien-Bridge oscillator with battery operated and do the testing, right? Applications are there. Similarly, relaxation oscillator, I think I have already discussed this. Blinking lights and electronic beepers. blinking lights. But again, blinking lights is in hertz, right? Electronic beepers, that also in hertz audible range, right? Those things you can consider this relaxation oscillator. We don't want to bring very high complex things into the plate and analyze. That's too much. Start with simple thing, gradually progress. It is easy for you. You can digest better. That is what our education system is, right? We don't learn differential equation in primary. We get to know our letters, numbers first. Then we play with those numbers, letters, bring words, and gradually you increase your skill set, right? Same thing. Right. This ring oscillator application is very vast. That means it can be used as a clock. A stable clock is still challenging for every application. Stable clock is still challenging. Challenging. What are the concerns? We have jitter. Jitter means uh, uh, some uncertainty in the output. You have the frequency, right? Suppose if we, after designing, when you measure it, you will have one output frequency, but the output frequency will not be the same all the time. It has some plus or minus, right? That is what we call jitter, clock jitter. If you if you put the eye diagram, if you plot the eye diagram, taking what you have to do is trigger at the positive edge and plot it in the middle. So you will see sometimes the positive edge goes to the left side, right side, the width of that, the width of the zero crossing or the width of the middle crossing, that is the middle point of the logic 0 and logic 1 or high and low. How much time it deviates compared to the period of the clock. Compared to the period of the clock. So plus or minus how many percentage time? Say the deviation is 10 nanosecond. My clock is 1 megahertz. So 1 megahertz means period is 1 microsecond. I have a deviation 10 nanosecond. So 10 nanosecond divided by 1 microsecond, roughly around 1% of the period, right? So that is the measurement. So 1% means it's much better. The low quality design becomes 2%, 5%, 10%. That becomes a serious issue in the digital design. If you take some digital subjects later, probably I will discuss those things, what kind of issues we will have there. Okay, but at this time, it is important to design low jitter clock modules. So in order to have low jitter clock modules, it is important to match the load as well as match the gates. Similar gates we have to use. Okay, there are some design challenges. We are at the very beginning, right? But however, the first step is to bring the silicon out and measure it. It may be successful, may not be successful. If we are successful, that's fine. But as long as it is switching, we can say clock is working. Then what is the next question? Quality of the clock. How much jitter we have? What is the duty cycle variation? We can measure it in the lab, right? Okay, I stop my lecture today with this. We will continue the next Tuesday. Okay, but anyway, section 1 is completed already. We will start with section 2 in the next session. If you have any questions, you can ask. Otherwise, we can wind up. Thank you.
Recording stopped.
Excuse me, sir.
Yes. Yes, I can hear you.
Sir, can I ask a question?
Sure, sure. Please go ahead.
So you mentioned earlier about tape out.
Yeah.
I'm not very knowledgeable about like how those get made. Like, can we get a custom chip made or something? I'm not very
No,
knowledgeable.
no, that is digital design. Custom chip means it is functionality is, I mean, the design procedure is customized. Okay. I am not sure what you mean by custom chip here, but that is, it has a different meaning. But taping out clock module at this level is more appropriate for you. But if you bring some other design into this picture, probably, I'm not sure the complexity of that because I have no idea. But if you have any other simple design, that is not part of this analog circuit design. Clock module is not digital. Basic gates are not digital. Their output is digital. That is the starting point for digital design. But those basic gates and clock modules are designed in analog way. That is why we talk about those modules in analog circuit design.
Okay, sir. So does taping out mean like designing? Oh,
Yeah, the design part is very simple. It won't take more than 6 hours or 9 hours, right? But there are standard procedures. That is very easy. Don't worry about that. It's just following. If you put a simple code there, it will do all the job for you, and we can tape out. Okay, that means we have to send that file to this particular location. They will do the design for you, right? I can guide you some. I can bring some other people into this picture if you are interested in. That's a separate matter. But first thing is whether you want to do it. Because we have to make sure that the complexity and the work is sufficient within the allocated time frame, allocated time slots. Do I answer your question or you have something else to?
yes, sir. You answered it. Thanks.
Okay, bye. Yeah. Any other questions or any other concerns? If not, I wind up this meeting.